Okay. Hi, everyone. Okay, so today I'll talk about infinity and uncountability, as well as a completely new proof technique which is called diagonalization. Okay, so So set theory actually started in the end of the 19th century with the work of George Cantor. And the way it started was, so before George Cantor, actually sets were known, but it wasn't really, this wasn't really a mathematical discipline. And it was after George Cantor started looking at infinitely large sets and realized that there was something very interesting about them, that set theory really became a discipline by itself. And so to understand this, let's look at this very simple example. Okay, so let's say that you have a hotel whose rooms are numbered 1, 2, 3, and so on. Just keeps going. It's an infinitely large hotel. And this hotel is actually called Hotel Z+. Okay? And one rainy night, it's completely full. So every room is occupied. And then so each of these rooms is occupied. And then in the middle of the night, 0 shows up and is looking for a room. Okay, so the innkeeper sort of says, look, I'm sorry, the hotel is completely occupied, we can't accommodate you. But his wife was a good mathematician. And she says, wait a minute, I think there's a way to deal with this. And so what she says is, well, let's do this. Let's take 0 and put him into room number 1. And now, of course, we have to move the occupant of room number 1, so let's move that guy into room 2, and take the occupant of room 2 and move that person to 3, and we just keep going. And now, of course, everybody is accommodated. Why? Because if you look at an arbitrary person J, who happens to be in room number J, well, that person is just going to move over to J plus 1. Right? So if you name any person, they're going to be accommodated. Right? And so what that tells you is that if you look at the set of natural numbers, which include 0, then it has the same cardinality, it has the same number of elements as the positive integers, which does not include 0. Right? So somehow it's saying, you have a set, and you have a set with one more element, and they have exactly the same number of elements. Right? So when you have something that's infinitely large, adding 1 to it doesn't change the cardinality. Okay? So now, that was not bad, but then, the following weekend again, it's really another bad night, and this time actually what shows up at the hotel is, the hotel is completely full, but now all the negative integers show up. Okay, so not only does 0 show up, but also -1, -2, -3, and so on. Infinitely many other people show up. And again, the innkeeper sort of says, well, we can accommodate you 0. That's okay, you're fine. But everybody else, all the negative numbers, they'd better go find some other place. And again, the innkeeper's wife says, well, actually, I think there may be a way to accommodate everybody. Okay? And so to understand how you can accommodate all the negative integers as well in only these rooms, right? So these rooms only go from 1 up to, on the positive side. And yet, somehow you can accommodate everybody to the negative, all the way to negative infinity, right? And so to see how this might be possible, just to get some intuition for this, okay, we might look at a different hotel, which is called 2z plus. Okay, it happens to have is it 2z plus? Okay, it just happens to have even numbered rooms, so 2, 4, 6, 8, and so on. Okay, but now the claim is that you can always take, if you have people number 1, 2, 3, 4, and so on, all of these people show up. You can accommodate them all into these rooms. And the reason you can do that is you'd put 1 in room 2, 2 in room 4, 3 in room 6, and so on. So you put each person in the room whose number is twice as, is twice the value, right? And of course, everybody gets accommodated. And similarly, if you had only the odd rooms, you can also accommodate everybody. But now that should tell you that you can take all the integers, plus and minus, and accommodate them in all the rooms from 1, 2, and so on by splitting them up into evens and odds. Okay, so now, in order to make sense of all this, in order to understand why all this is okay, we have to actually formalize all this and make sure that we understand what we are talking about. Okay, and so that's what we are going to do next, but after a question here.
How can a hotel infinite room be completely full? Would it always have more rooms?
Yeah, but there are also more people. So there are infinitely many people and infinitely many rooms, and it's completely full in the sense that for every room there's a person, for every person there's a room. It's just completely full.
But you showed that you could always have more room for more people.
Yes. Yeah, that's the whole point of infinity, and that's what makes so that's why when you talk about infinity, the mind boggles. And the point of Cantor's work was he was able to take this whole thing where the mind boggles, and he was able to make sense of it. And so what we are going to do today is we are going to see how to make sense of all this. Okay, so far I've been talking about this informally, and now we are going to go ahead and talk about it more formally. Okay, so that it'll become clear to you what the rules of the game are, right? And how we trust not our intuition, but how we can actually formalize all this so that it makes sense. And this was the genius of Cantor. Okay, and this is what launched set theory as a discipline. Okay, any other questions? Okay, so now to make sense of all this, what we're going to have to do is go back and think about what we mean by counting something. So how do we actually count? And the answer lies in, back in kindergarten, right? In kindergarten, when you counted, you sort of to tell whether a set of beads was, they were the same number as a set of marbles. What you would do is sort of place them next to each other and see if they checked off, if there was a 1-to-1 correspondence. Okay, so we say that two sets A and B have the same cardinality. The cardinality of A equal to the cardinality of B. So the number of elements in A equal to the number of elements in B, if and only if there's a bijection. There's a bijection which maps A to B, right? So the way you would say that these two sets, 1, 2, 3, and X, Y, Z, have the same number of elements is by saying, well, there's a function, f, which maps 1 to X, 2 to Y, 3 to Z, and it's a bijection, and therefore this set has the same cardinality as that, right? And it's obvious it works for finite sets. Okay, so this was actually a definition that Cantor came up with. He said, well, this is what we really mean when we say two sets have the same number of elements in them. And now let's use this definition for infinite sets and see what we get, right? Because it's obviously the right definition. So let's try to see what we get. And the answer we get is, well, you have a function f such that n, the natural numbers, get mapped to z plus. And what's this function? It's a bijection between the natural numbers 0, 1, ... to z plus, which is 1, 2, ... Right? And the way it works is f of x equal to x plus 1. Right? It's a bijection because it has an inverse. Right? And the inverse is g of x equal to g of y equal to y minus 1. Right? Okay. Now, what we're also claiming is that, in fact, there's also a bijection f which maps the natural numbers to all integers, z. Right? And what would this bijection look like? So it's, if x is even, then we map it to x over 2. So that maps, so we have 0, 1, 2, ... And we are mapping it to 0, 1, 2, 3, minus 1, minus 2, etc. And so the way we are doing it is 0 is getting mapped to 0, 2 is getting mapped to 1, 4 is getting mapped to 2. And now we want 1 to go to minus 1, and 3 to go to minus 2, and so on. So how do we do that? Well, what we could do is, if x is odd, we could map it to x plus 1 over 2 minus of that. And now you can see if x is 1, x plus 1 over 2 is 2 over 2, which is 1. And then if you take minus of that, it goes to minus 1. Right? If x is 3, 3 plus 1 over 2 is 2. And then you take negative of that, we go to minus 2. Right? And so you can see it's a bijection. It maps the natural numbers to the integers. Okay? So now you can think, well, what do we have to do to get a larger set? Okay, so we tried adding one element, we tried going infinite in both directions. Here's something we can do. We can move on to the rational numbers. Now, the reason there ought to be more rational numbers than natural numbers or integers, it's obvious, right? So here's the number line. There's 0, 1, 2, 3, etc. And where are the rational numbers? They're everywhere, right? So they're dense. You know, between any two rational numbers, you can find another one, right? So they're just all over the place. There are infinitely many, and they're just completely densely populated in here, right? And so you would think surely there are more rational numbers than there are natural numbers. So here's the fact. The number of rational numbers is exactly the same as the number of natural numbers. Okay? It's no different. I'm sorry? Okay, and so to show this, what we have to do is, you see, we said, Cantor told us that the way we say that two sets A and B have the same number of elements is if we can show a one-to-one correspondence. We show a bijection between them. That shows that they have the same number of elements. Well, there's something else that Cantor and Bernstein told us. Okay, so this is called the Cantor-Bernstein theorem. And what it says is, how do we show that the cardinality of A is less than or equal to the cardinality of B? Okay. So the way you can show that the cardinality of A is less than or equal to the cardinality of B is just by showing a one-to-one function from A to B. Okay? It doesn't have to be a bijection. So in other words, if you can show a function f which maps A to B in such a way that it's one-to-one, meaning this is not allowed. There are no collisions allowed. It cannot be many to one, right? So if you have any point here, it has at most one thing that maps to it. Okay? So what prevents this from being a bijection? It's not onto. So in fact, what prevents it from being a bijection is we might have other points in here which don't get hit by anything. And that's why we are saying A is less than or equal to B. Right? Okay. So F is one-to-one, but may not be onto. So it's not necessarily a bijection, but still, if it's one-to-one, then what we are establishing is the cardinality of A is less than or equal to the cardinality of B. So now how would you show that cardinality of A equal to the cardinality of B? Well, you'd show A is less than or equal to B, and B is less than or equal to A, implies A equal to B. Okay? What does this mean in terms of functions? It says, so what the Cantor-Bernstein theorem says is, suppose I can show you a function, a one-to-one function which maps A to B. And suppose I also give you a one-to-one function G which maps B to A. It's one-to-one. So G is one-to-one, F is one-to-one, implies there exists a bijection H which maps F A to B. Okay? So it's telling us, suppose we know that B is less than or equal to A, and we know that A is less than or equal to B, then we know that A equal to B. Right? Does it make sense? Okay, this is why it's okay. This is why intuitively we say, this is what's telling us A, the cardinality of A is less than or equal to B. That's telling us B is less than or equal to A. And Cantor-Bernstein really tells us, when we establish A less than or equal to B and B less than or equal to A, it implies that A equal to B. Okay? Cantor-Bernstein is completely trivial to prove when A and B are finite sets. But when they are infinite sets, it's not so easy to prove. Okay? So we'll just assume it for our purposes. Okay, so how did we get to Cantor-Bernstein? We were trying to show that the number of rational numbers is equal to the number of natural numbers. So there's something that we can say very easily. So the thing that we can say very easily is that the number of natural numbers is at most the number of rational numbers. Everyone see that? Because every natural number is a rational number. Right? So you have a one-to-one map where you just map each natural number to itself. And that's okay. That's a rational number. Okay, so the hard part is showing that the number of rational numbers is at most the number of natural numbers. Okay, so let's prove it in two ways. We'll prove it first by picture, and then we'll prove it by a different method. So the way we do this is we're going to say, look, the way we can represent a rational number is by an ordered pair. Right? A rational number Q is of the form A over B. It's a set of all A over B such that A and B belong to the integers. B is not equal to 0. Okay. And so the way we can represent it is by numbers, by ordered pairs here. A over B, A over B. So B is not equal to 0 tells us we are not on this line, right? Yeah. So it's all of these points. Now, of course, every rational number will be represented infinitely many times here, because you have the rational number 1 over 1, 2 over 2, 3 over 3, 4 over 4. They're all the same rational number, right? So you take any rational number, you multiply both the coordinates by 2, and you get the same rational number. But the point is, every rational number is represented in here. And the way we'll map the rational numbers to the integers is just by, or by the natural numbers. What do the natural numbers look like? Well, the natural numbers look like that, right? It's 0, 1, 2, ... Okay? And so what we want is something like this to include all of these points. Well, actually, not all these points, only, all we want is all these points which correspond to, which include each rational number once. But of course, if we include all these points, we are doing even better, right? So if we can say, we want to say that the natural numbers there are at least as many of them as there are rational numbers. So if instead of just covering all the rational numbers, we also cover lots of infinitely many other points, we're actually showing that natural numbers are even bigger. Right? So it's even better for us. So how do we show that? Well, how do we cover all these points with something which looks like that? Yeah, you take a spiral. So you just start from here, and you go out, you do that. Okay? And so now, remember what it meant to show that there's that the set of rational numbers is less than or equal to the set of natural numbers. It means showing that there's a function which maps Q to N such that it's 1 to 1. Okay? Sorry. Yeah. And so what are we doing here? Well, what we're doing here is we're saying, look, let's map this to 0, that to 1, 2, 3, 4, 5, 6, 7, etc. Right? And now we are saying each rational number which occurs, every rational number occurs somewhere along this spiral. And where does that rational number get mapped to? It gets mapped to a unique natural number. Right? No other rational number is going to get mapped there because that's the only one which is this distance away. Right? Every other one is going to be mapped to something either smaller or larger. Right? So it's 1 to 1. Right? So that shows that the number of rational numbers is also equal to the number of natural numbers. Okay? All right, so well, maybe this whole theory of infinity is not that interesting after all. Maybe all infinities are equal. Okay? So where do we go to find, something larger? Oh. Okay, so here's one way we can generalize everything we've done so far. one thing we can do is we could think of the rational numbers as corresponding to polynomials of degree 1. Right? So if you have something of the form a over b, right, we can write that as ax plus b, right, where a and b are integers. So there's sort of a correspondence between these two. Okay? Now, what if instead of that, we looked at polynomials of every degree? Okay, not just degree 1, but any degree at all. So we look at, so a over b, we could think of this as a comma b. That's another way to look at this, right? And now we could just look at every possible finite sequence. So a sequence of the form a, b, c, d, e, right? Arbitrarily long such sequences where these are integers, right? This would correspond to a polynomial of degree 4, ax to the 4 plus b x cubed plus c x squared plus dx plus e. How many such polynomials are there? Or how many such sequences are there where I can take the sequence to be arbitrarily long, right? I can take it to be 1,000 or 1,000,000 or as long as I want, right? All possible such sequences, any finite number, right, that we want. So how many such sequences are there? Maybe that's a larger number. So here's one way to think about it. Okay, so again, the claim is this number of sequences is exactly the same as the number of natural numbers. And the number of natural numbers, by the way, is called, because it keeps coming up so often, it's called something, it's called countable. Okay, so we'll say the number of polynomials is countable. Okay. So how would we show this? So here's a trick. So the first thing we are going to claim is that if you look at the set of all finite binary strings, this is countable. This is the same as the number of natural numbers. So what's the set of all binary strings? They're of the form, well, the empty string, the string 0, the string 1, string 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, etc. You get the idea. It's all possible finite strings of zeros and ones. So how do we know that this is countable? How do we know that this is the same as the number of natural numbers? Well, what we could do is we could take each of these and put a 1 in front. So if you take the empty string and you put a 1 in front, you get 1. If you take this one, you get 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, etc. And now you get to see, right? These are all binary. This is 1, 2, 3, 4, 5, etc. in binary. So we got not the natural numbers, but the positive integers. But the number of positive integers is exactly the same as the number of natural numbers. So it's all countable, right? So what we did was we placed 1 in front to get set of positive integers, and therefore it's countable. Right? So we wanted to show this set is countable. That's a set of all finite binary strings, and we just looked at it the right way, and we saw it was the same as the set of positive integers, which is the same as the set of natural numbers. But now, once you know this, once you see that the set of all binary strings is countable, you can apply almost exactly the same argument. Okay? So I'll make another claim, and this is the proof of this is an exercise. If you look at the set of all finite ternary strings, okay, meaning strings like empty string 0, 1, 2, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, etc. Right? So all possible strings that you can get with the alphabet 0, 1, 2. This is also exactly the same as the number of natural numbers, almost by the same argument. Right? So you have to think a little bit harder. But now, once you know this is the case, I claim that you also know that the set of all polynomials is countable. Okay? So now, why would this be the case? Why would it be true that as soon as we know that this set is countable, we also know that the set of all polynomials is countable? I'm sorry? By induction. Actually, it's just by looking at it. So see if you can see it in a certain way where it becomes clear that it's the same thing. Okay? In fact, this is a very good point to think about. So let's take a 1-minute break as you think about it, and then we'll resume once you've thought about it. Okay. Let's see. So, how many of you think you figured it out? Okay, so let me just say a little bit about this. So let's go back and remember what we are trying to show. We are looking at polynomials whose coefficients are natural numbers. We could also let them be integers because natural numbers, integers, it's all the same. So number of polynomials with integer coefficients is countable, right? So we want to say there are as many polynomials with integer coefficients as there are natural numbers. Okay, so how do we show that? Well, what we just claimed is that if we look at the set of all finite ternary strings, that's countable. Now I claim that the finite ternary strings, you can look at them in a certain way where they start looking like polynomials. Okay, so how do you look at that? So let's say you had the polynomial 4x cubed plus 2x squared plus 3x plus 1. Okay, so another way of saying this is it's a sequence 4, 3, 4, 2, 3, 1. Okay? So let me write this down in a certain notation. So what's 4? It's in binary. It's 1, 0, 0. Right? And then we want to put a comma, so we don't have a comma, let's put a 2. And then what's 2? It's 1, 0. Okay, we don't have a comma, so let's put another 2. And what's 3? It's 1, 1. 1. Okay? So I claim that this is another way of writing that. And therefore these three are the same object, right? If we are counting, if we want to count these, we may as well count these. It's the same thing. Right? Yeah? And now do you see that they are, if this is countable, then this is countable because they are exactly the same number of both. Right? Yeah, does it make sense? No? No? Okay. Okay, so okay. So maybe okay, let me do this. Let me just wait for 30 seconds and see if it makes sense. And then if not, I'll let somebody ask a question. Okay. Okay. There's a question back here. Yeah. Oh, yeah, very good. Okay. So before you ask that question, let me just say one thing. What we are trying to do, the thing that we are trying to do is to show that the number of polynomials is less than or equal to the number of natural numbers. Right? So now, because the number of polynomials is clearly at least as many as the number of natural numbers, right? Because all you have to do is look at the polynomials of degree 0, and that's already as many as the natural numbers, right? Okay, so the only thing we want to do now is to show that the number of polynomials is no larger than the number of natural numbers. So how do we do this? We show that there's a one-to-one function from the polynomials to something which is as large as the natural numbers, which is this set of finite ternary strings. So I want to map every polynomial to a distinct ternary string. How do I do that? I just showed you a mapping, right? I just showed you a mapping. So if I have a polynomial, I write out what are the coefficients, and then I write them out in binary. And instead of separating them by commas, I separate them by 2s. And now I claim that this particular string is not going to be mapped onto by any other polynomial. Right? How do you know that? How do you know no other polynomial can possibly end up here? Because you can read off the polynomial. right? If I showed you the string, suppose I hid this from your side. So you didn't know this 4, 2, 3, 1. You did not know this polynomial. I just showed you this string. Can you tell me what the polynomial is? Yes, obviously, right? You can say, well, the 2's, these are the commas. This must be A, it's 1, 0, 0, that's 4. This is B, it's 1, 0. 1, 1 is 3. 1 is, right? So you can read off the coefficients one by one. So you know that it's 1 to 1. Right? You can't have two different polynomials that map to this. And therefore, the number of polynomials is less than or equal to, etc. Yeah.
Couldn't you have done this in the binary? So 1, 1, 1, 1, 0. 1,
Oh yeah, you're right. We could have done it in binary, except then we would have. You're absolutely right. So we could have done this with binary as well, and then the encoding would have been like this. This would have been. Which one should we use as commas? Let's use zeros as commas, right? So 4 would be 1, 1, 1, 1, and then you put a comma, and then 2 would be 1, 1, then a comma, 3 would be 1, 1, 1, comma, 1, right? That would have been fine. That would have worked too, right? Because we don't have to be efficient. We have infinity to play with. Yeah. In which one? In which case?
The binary one?
In this one, where does it break off? It breaks off at the zeros. So these are commas. So 4, in order to write 4, we just put down 4 ones. Yeah? So we were being very inefficient in encoding. Okay? Yeah, back there. I'm sorry? Oh, what if it was 0? Then you would just have two 2's next to each other. Yeah? Yeah.
Are we also considering polynomials of infinite degree?
No, these are all, a polynomial is just a finite degree. Yeah? Yes?
So, would it be correct to say that mapping is 1 to 1 but not onto?
Is it onto?
Not onto.
Is it not onto? Yeah. So is there? Probably not. I mean, it depends upon how you define it. We wouldn't have well-formed polynomials, right? So if you have just 2's next to each other, then there would be 0 times this plus 0 times that, and it's the same thing as, right? So it's not completely clear how to make sense of that. Okay. So now, so far everything we've touched turns out to be countable. It's, every kind of infinity we've seen is just as big as the number of natural numbers. So what do we have to do to go beyond? Well, it turns out the answer is again surprising. It turns out that the real numbers are uncountable. And this was the surprising discovery that Cantor made. Okay, and for this he gave a truly beautiful proof. But before we look at the proof, let's see why this should not be true. Right? It has no business being true. The reals have no business being uncountable. And the reason they have no business being uncountable is, again, look at the number line. So you have 0 there. And now, what do we know about the rational numbers? What do we know about the rational numbers? They're dense. Right? So, meaning they just completely, it's completely full of rational numbers. Right? Meaning what? So, for example, they are dense in the real. So if I give you 2 real numbers, here's R1, there's R2, and these could be arbitrarily close to each other. Right? It doesn't matter how close they are to each other. I can always insert between them a rational number. Right? So there's always some rational number, little q, equal to a over b, which I can insert between them. Yeah?
Does this relate to the continuity function versus continuity?
You mean the uncountability?
Yeah.
I don't know what that would mean, though. Right? So I'm not sure what you would mean. But let me go on, and we can talk about this later. To me, this is an extremely paradoxical situation. Why are there more real numbers than rationals? We'll prove it, but it's completely counterintuitive. And the reason it's counterintuitive is this, right? So if you have a finite set, so let's say we had a finite set and we lined these guys up. And suppose I told you that between every pair of these elements, there's one of another kind. So there's another set of these round elements, and between any two crosses, I can put one of these guys. Okay, so between every pair of them, I can put one of these guys. Maybe more, but at least one. So then you know that the cardinality of this round set is almost, it's at most one smaller than the cardinality of this cross set. And if you're dealing with infinity, one smaller is nothing, right? So if this was a finite set, and I told you between every pair of these, there's one of those, then the cardinalities would be essentially equal. But with infinity, it's not, right? Between every two real numbers, there's a rational number, but we don't know, but still the real numbers are infinitely more than the number of rational numbers, because there are only as many rational numbers as the number of natural numbers, but the real numbers, there are more of them. You just cannot put them into one-to-one correspondence with each other. There's no bijection. Okay? So, by the way, what do we mean by a real number? What is a real number? There are many ways of defining it. For our purposes, it's an infinite decimal expansion, or decimal binary expansion, whatever we want, right? So it's an infinite decimal expansion. Right? So R might be 29.5782 and this goes on forever. Right? So now you can see why between any two real numbers there's a rational number. Because if they are different from each other, they must differ in some finite place. And now you can always interpose a rational number between them by just going out a couple of more places and making sure it's bigger than this one and smaller than that one. Right? You have room to play between the two. Okay? Okay. So now, how would we show that there are more real numbers than rational numbers? Okay. So, this is where Cantor came up with a completely new kind of proof technique. It's not a proof technique we have seen so far. It's not a proof by contradiction, not a proof by contraposition, it's not a proof by induction. It's something completely new. So he invented a new proof technique, and it's called diagonalization. And it's a very powerful proof technique. It's a very interesting proof technique. And the way it works is like this. So we assume so to prove that the rationals are uncountable, we prove it like this, by diagonalization. So we first start by contradiction, and we assume that the real numbers are countable. Assume the reals are countable. So we assume for contradiction. Okay? Now what does it mean they're countable? It means that there's a bijection between the natural numbers and the real numbers. Okay, so you can number them. You can number the real numbers, the 0th one, the first one, the second one, and so on. Okay? So let's go ahead and number them. So there's the 0th one, first one, second one, etc. Actually, for the purposes of this, we are going to prove something stronger. We'll prove that the real numbers between 0 and 1 are already uncountable. Okay, so we're going to prove not just that the reals are uncountable, but the reals in the interval between 0 and 1. Those are already uncountable. So assume for contradiction that the reals between 0 and 1 are countable. Okay, so now we can write them, every number between 0 and 1, we can write as an infinite decimal expansion. So it's going to be 0.2138 ... 0.5263 ... etc., right? 0.7777, 0.8122. Okay? So you can write out all these numbers. These are all the real numbers there are between 0 and 1. Right? Okay. Now, what Cantor showed through this diagonalization argument is how to construct a real number which is not in this, which is nowhere in this column. Okay, so now the proof, the next step of the proof is we'll construct R, which is a real number between 0 and 1, which is not on this list. Okay? And that's a contradiction. Okay? Now, in order to do this, what Cantor is going to do is he's going to be looking at, so he has two numbers. He has a number on this list, 0.523157 ... and then he has this real number R, okay, which looks like point something 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 something. Okay, except in order to show that this real number is not that one, all he can do is look at it in one window like this. He can look at some digit of this number and that same digit of R. And he wants to show that these are not equal. So what condition would you want to make sure that they are not equal? What would guarantee you that this R is not the same as that number? If all you saw was, everything else was hidden from you, the rest of this number was hidden from you. So for all you know, this might be 5231, etc. You don't know what the rest of the number is. All you can see is this digit of it. So obviously it should not be a 5. But does that guarantee that these two numbers are not equal? Almost, right? If you remember how real numbers behave, it almost guarantees it. Right? Because what if this number had been 4? And this was 9999999 ... And then that's the same as, this is equal to the same thing, 5,0,0,0,0,0. Right? You remember this? Oh, okay. So remember, okay, so let x equal to 0.999 ... Remember, so now, what's 10x? Equal to 9.99. Subtract. So you get 9x equal to, this minus this is 9. So x equal to 1. Right, so 0.999, if you keep going, it's the same as 1. Right? So if all you got to do was look at this digit, then it's not enough to say that this is not the same. You have to say, well, it's not the same as this, and it's also not one smaller. As long as it's different from that, you're safe after that. Right? Because the most you can do with this, with the rest of this, is make it equal to, one more. Right? So as long as you stay at least one away from that, you're fine. Okay? As long as you can say, well, this is 5, this is not 4 or 5, then these two numbers are different. Okay? Yeah.
So what if it was 5,999,999? That was 6,0,0,0,0.
Oh, yeah, you're right. So it cannot be within 1. So it cannot be 4 or 5 or 6. So you have to be at least 2 away. Right? So you cannot be within 1, and that would not be okay. Okay, so that's the only thing we have to be careful about in constructing this number R. So how do we construct the number R? So this is where the name of the technique comes in, diagonalization. So we pick the diagonal. Okay? And so what do? To construct this number, we pick this diagonal. So we have 2, 2, 7, 2, dot, 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 dot. Okay? And now what are we going to do? We just want to change each of these digits by at least 2. We can't leave it, if we change it by 1, we don't know whether we change the number, but if we change it by at least 2, we are okay. So what we're going to do is add to each of these digits 2 mod 10. Right? So we add 2 mod 10 to each digit on the diagonal. Of course, you could add 3 if you wanted, or 4 if you wanted. It's all the same, right? Okay, so what do we get? We get a new number which is 0.4494 dot dot dot. Okay, well, let me just to make it more interesting, make this a 9, and so now this would be not 9. 9 plus 2 mod 10 is 1. So, okay. So you get the idea, right? You just add 2 mod 10 on the diagonal digits, and this is equal to R. And now I want to claim R does not exist anywhere on this list. How do we know that? It's this argument, right? So if you claim that R is one of these numbers, okay, so you claim that R is one of these, well, like this one. How do we know R is not this number? Yeah, you just look at it. So the fourth position here was 1, here it was 9. How did we get 1? We added 2 mod 10. Right? So we made sure that if we were looking only at this diagonal element, that we are off by at least 2. So we know that this number cannot be equal to this one because they don't agree on this diagonal element. But for every number on this list, there's a diagonal element. There's the digit that occurs on the diagonal. And we know that R differs from it on that digit by construction. Right? And therefore, R does not belong to this list. Okay? So what we've managed to do is construct a number R, which is in this between 0 and 1, which is not on the list, by this diagonalization argument. Contradiction. Therefore, the real numbers between 0 and 1 are not countable. Okay? Yes?
So that's like showing that there's an infinity plus 1 real.
Well, there are more than 1, because if there was only 1, you go from natural numbers to the positive integers. Or vice versa. You just get 1 more, and then it's the same thing, right? So with infinity, it's not just 1 more. This is you get, you're getting a larger infinity.
Wait, so that's weird. So this number was not in the original infinite list?
Yes. And in fact,
even though it's made up of all the numbers that could appear as a...
well, no. So this was not. We made an assumption first, right? We assumed that you could take all the real numbers between 0 and 1, and you could line them up this way, right? Having made that assumption, then we showed that there's a new real number which doesn't fit on this list. Now, and then we said, what could go wrong? Well, what must have gone wrong is that this assumption was false. Okay? So, which means that you just cannot list all the real numbers between 0 and 1 this way. Which means that there's no bijection between them and their natural numbers. There was a question? Sorry, do you not have a question? Okay. Yes. It's on 2? What does it mean? Oh, could you produce all the reals between 0 and 1? Well, you certainly could, because you can let this diagonal be anything you want. I showed you one way of creating this number R by just adding 2 to everything on the diagonal. Okay? But now, of course, you have other ways of creating this number, but in this particular way of doing it, I just showed you one particular number, right? And now, of course, you could do other things with it, and would you get all possible real numbers? I'm not sure. Probably not. Yeah? Yeah.
I have another question, because you could, in the same way that you showed all the polynomials accountable, in that there's always a binary string that can map to the
Yeah.
all the coefficients. So why can't you treat all the decimal places as coefficients and then map it to a binary string?
Well, remember, okay, so the question was, what was different about these binary or ternary strings here? What was different here was these were finite strings. They always end somewhere. They're arbitrarily long, but each of them ends. Whereas when we are dealing with real numbers, they are infinite expansions. Right? And so this is just qualitatively completely different. Yeah? Okay. Okay, now, there's one more thing I want to talk about today, which is one more application of diagonalization. And today we'll see it as an application of diagonalization, but then in the next lecture we'll see it from a different viewpoint. Okay, a different viewpoint which might give you more, a different intuitive viewpoint. But today we are just going to see it as an application of diagonalization. So the thing that we'll prove is this. Something that would be extremely useful to have, if you're writing a compiler, is to understand when you are given a program, does it halt or does it go into a loop? Or even if you're given a program and it on some input, you're running this program on input I, and you want to know, does it eventually halt or does it stay in a loop? Does it go into a loop? Right? Does it loop forever or does it halt? Okay? And so one of the great things that Turing did, okay, is of course, first of all, he defined this model of computation, right? Long before a computer existed, he defined an abstract model of a computer called a Turing machine. And then he showed something very interesting about a Turing machine. He showed that you can program it. In his language, he showed that there's a universal Turing machine. Okay, there's a Turing machine to which you can give other programs, other Turing machines as input, and it interprets it for you. But then the other thing he showed is that Turing machines are not all powerful. Programs are not all powerful. In fact, what he showed is that the halting problem is undecidable or uncomputable. What should I call it? Let me say it differently so that I can say it as uncomputable. Answering this question is uncomputable. Okay? There's no computer program that can reliably on input P and I tell you that whether P halts on input I. Okay, there's just no way of doing this. And the way he proved this was by this kind of argument. Okay? So let me say a couple of things about this proof that the halting problem is uncomputable. That it's you cannot give an input a program and an input to it tell. There's no systematic way of telling whether it's going to eventually halt or not. Okay? Even though it would be extremely useful in analyzing programs, this is just something you cannot do. Okay, the one concept that comes into all this is this notion that when you write a program P, it's a program, but also it's data. You can, whether you think of it as a program or as data, just depends upon your viewpoint. Because a program eventually is a string, right? You could write it out in binary, and then it's just a piece of data, right? If you want to interpret it as a program, that's your right to do. It's your right to do so. But you can also interpret it as data, okay? And the fact that it can be interpreted as both plays a really central role in the proof that you cannot solve the halting problem. Okay? So how do you show that you cannot solve the halting problem? Here's a proof. So again, suppose for contradiction, you have a program, test halt, that on input, this program P and an input to it, it outputs H if P of I halts, and L otherwise. Right? So it loops wherever halts, right? It tells us which one it is. Okay. So suppose such a program exists. Now what can we do with it? Well, here's what Turing did with it. So what Turing said was, look, whether something is a program or whether it's data, you really cannot tell. Right? So now let's run this let's define a new program, Turing, which takes as input just P, a program. And what it does is it says, if test halt on input P. So what does this mean, by the way? It's saying, let's test what happens when you take the program P and feed P into it as input. Okay? So something weird is going to happen now, right? I mean, how can you feed a program to itself? There should be a law against it. But, okay, still, you do it, and then what happens? So now, if you really want to make mischief, what you would do is, if this equal to halt, then what would you do if you were trying to make mischief? Then loop forever. Right? And if it is equal to L, then halt. Okay, so far, okay, that's a funny thing to do, but how bad can it be? Okay? Well, so let's see how bad it can be. What happens when you run Turing on input Turing? Right, it's a program. You wrote it. Okay, so you look at what the code is, and now you feed it to itself. What ends up happening? Well, what it does is, it says, if test halt PP, right? If test halt Turing. If Turing on input Turing halts, then it loops forever. And if Turing on input Turing loops, then it halts. Okay, if Turing on input Turing halts, then it loops forever. If it loops, then it halts. There's a contradiction there, right? I mean, something is completely wrong now. Okay, so what could have gone wrong here? Well, it didn't go wrong here, must have gone wrong somewhere here, right? Okay, this is where it went wrong. Suppose for contradiction. So that went wrong. So there's no such program test halt. Right? So we showed that you really cannot test for halting. If you had such a reliable test, then you could build upon it, and you could build upon it, and then you could create this monster. Right? Okay, so now let's go back and see what's the proof technique that we used here. Okay, so I claim it's diagonalization. So what's the diagonal? What is it a diagonal in? So we are going to make up a figure just like this, right? Except the question is what's on this side and what's on that side. Right? Okay, so what we are going to do out here is we are going to write all the programs, all possible programs. How many programs are there? We didn't talk about that, right? How many programs can there be? It's countable, right? It's a countably infinite number. Why? Because a program is a string, right? It's a finite string, finite binary string. But how many binary strings are there? How many finite binary strings are there? It's only countably many. So there's no more than countably many programs, which means that we can take all the programs and we can say what's the first one, what's the second one, what's the third one, and so on, right? Because there's a one-to-one correspondence between the programs and natural numbers or positive integers. Okay, so we write them down. There's P1, P2, P3, ... right? That's all possible programs. Right? There are infinitely many of them, and we just write them down in sequence. Then what do we do on this side? Well, let's write down all programs, P1, P2, P3, ... Okay? And now what should we put in here? So what should, if we have Pi, Pj, what should this entry be? Let's make it test halt Pi, Pj. Right? If we run test halt, we say, does program Pi halt on input P sub j? Okay? And now, what did we do when we created Turing? Okay, so we had some entries. So we had, this was halt, this was loop, etc. This was loop, halt, loop, halt, loop. Okay, so we had some entries here. And then how did we create Turing? So we went, remember, the input was test halt P, right? So we were going straight down the diagonal. And then what did we do? We flipped it, right? So we said, if this is halt, then we flip it to loop. And if it's loop, we flip it to halt. Right? Okay, so, and then what's our reasoning? We say, well, suppose that this was the output of a program. Well then, since every program is somewhere in here, this program must be somewhere in here. It must be P sub k for some k. This is Turing. Right? If it's a program, it must occur somewhere on this list. Maybe it's this particular program. But now look at this diagonal entry. Right? Whatever this diagonal entry was, Turing, we flipped the entry. Right? The way we defined Turing is we took all the diagonal entries and we flipped them. So whatever the output of Turing is, all these might be correct, but this definitely is not. The diagonal entry is definitely not correct, because whatever the answer was supposed to be, we flipped it when we created Turing. Right? And so by diagonalization, by that diagonal argument, we know that this cannot occur anywhere in this list. And therefore, there's no program that computes Turing. But that's the contradiction. That contradicts the fact that we said, if there's a program for test halt, there must be a program for Turing. Is it clear? Any questions? Okay, thank you.